concentration. Okay, what is mean by carrier concentration? Concentration in intrinsic. So we are solving in intrinsic semiconductor present at this moment. After that, we'll solve in extrinsic semiconductor, right? So what is mean by carrier concentration? Okay, what is carrier here? What is concentration? Oh, carrier concentration means number of electrons or holes in a for unit volume or volume you can take number of electrons or holes for unit volume in a intrinsic semiconductor. Okay, we don't know how many electrons are there, how many holes are there. Okay, if you are giving temperature, once you give the temperature, electrons, bound electrons in the valence band, breaking the bonds and they are jumping into the conduction band. Once they jump into valence band to conduction band, they are creating holes in the valence band, and these holes are free as well as and electrons in the conduction band, these also free. Because of these free charge carriers, we are getting the current in a semiconductor. Okay, right? Now carrier concentration means number of charge carriers are you can say these electrons are holes. Electrons are holes, you can say whatever. Okay, so here we are solving this. What is the equation? We are very important. This one we'll solve this one. Okay, first you understand this diagram, then you will clearly able to derive the equation part. Okay, this is the equation part. So this is conduction band. Okay, conduction band. This is lowest energy level EC, and this is valence band, highest occupied energy level EV. Right? So here also many states are there. Okay, already we are discussed many times. Okay, here also many states are there. Okay, these states extend up to minus infinity. Here also many available states are there. We don't know that states, how many states are there. Okay, these states also extend up to infinity. Okay, but convenient we are taking this is as a band. This is also band. This is conduction band. Okay, this is conduction band and this is valence band. Okay, valence band. Okay, now if you take intrinsic level, where will be the Fermi level lies? Where is the Fermi level in intrinsic semiconductor? Where do you draw this Fermi level?
Middle.
Yeah, middle of the band gap. Very good. Okay, this is the band gap. Okay, this is E. So this is Fermi level. EF you take. Okay, Fermi level means maximum field energy level at 0 Kelvin. But we are considering semiconductor at room temperature. That's why we are drawing at the middle of the semiconductor, because at room temperature some of the electrons here break the bond and jump into the conduction band. Once they break here, okay, once they break bond here, they leaves the hole. Okay, they leaves the hole and these holes are free in the valence band. These electrons also free. So like that, here free electrons are available in the conduction band. Okay, here free holes are available in the valence band. Now we are going to calculate how many electrons are available. Free electrons here, free electrons you have to take. You have to say free electrons available in the conduction band. Okay, in the conduction band, first we will calculate how many free electrons available in the conduction band. After that we will see how many free holes available in the valence band. Okay, that we will calculate today. Okay, so this is also some energy levels only, right? Energy levels are increasing. This is EV means this is some infinity lowest energy, and this is the maximum energy in the valence band. This EC is the lowest, this is the highest energy. The energy levels are increasing, right? This way it is increasing. Okay, this way it is increasing. So this is lowest energy level. If you go up and we will get the highest energy levels. Okay, this is the general thing. Okay, now now we will calculate density of electrons. Okay, density of electrons. So density of electrons, or you can say, or density of electrons are charge carrier concentration, or carrier concentration, or charge carrier concentration, whatever you can write convenient way. It's all are same, but different terminology, different terms. Okay, that's concentration. Okay, concentration. Okay, charge carrier concentration of electrons. Okay, we are calculating only electrons in the conduction band. After that, we'll calculate holes in the valence band. Okay, right. Now the formula is given by N is equal. This is N means number of charge carriers, that is electrons or density of electrons, you can say, in the conduction band. What is the lowest energy in the conduction band? What is the lowest
EF.
energy? EF, not EF. That is Fermi level. EC is the lowest energy. Okay, EC is the lowest energy. Okay, the Fermi level indicates mainly how many means how many electron. Suppose if you take entire semiconductor, where electrons are higher, concentration of electrons is high or concentration of holes is high. If which one is high, the Fermi level is goes to the that level. Means if you take entire, majority carriers are electrons. So Fermi level we will draw close to the conduction band. That indicates only which carrier concentration is higher in a semiconductor. What type of charge carriers are higher in a semiconductor, that will indicate. Okay. Here EC is the lowest energy in the conduction band. Okay. What is the maximum energy here? Maximum limit. If you see diagram, what is the maximum limit? This level, energy levels extending up to, we don't know how much
Yes.
distance. This one, man. This one. This is, we are drawing
Infinity.
this lowest energy, and these states are extending up to infinity. We don't know how many states are there. First at present, we don't know how many states are there. That's why we are drawing up to infinity. Infinite states are there. We are considering, but we don't know how many is there. So that's why upper limit we are taking a infinity. Okay, lowest energy of the conduction band infinity, EC, and highest infinity. Within this range, within this within this range, we are calculating how many electrons. Okay, this conduction band is extended up to infinity, and here how many electrons are there, we are estimating. Okay, for that, first this is the probability, the Fermi Dirac function, and density of states function, and this is dE. dE, why we are taking the, what is the probability density function? This Fermi Dirac function means what? Fermi Dirac function. You know Fermi Dirac distribution function. What it will gives the information? What information it will give? Fermi Dirac distribution. You have studied these distributions. What does it mean? Fermi Dirac means. So here, okay. If you don't know, okay. Z of E is the density of state per unit volume within the interval of, per unit volume or per volume you can take within the limits of E to E plus dE. That means E plus dE means what? We are taking a certain energy interval range. We are taking a certain energy interval range. Okay, this is density of states. Okay, density of states. Okay, density of states. What is mean by density of states? What is mean by density of states? Please tell me. Don't know? What is mean by density? At least leave it the density of states. What is mean by density? Density of mass, or if you take, what is the density in suppose if you take mass or something else?
Volume.
Sorry.
Mass per unit volume.
Yeah, mass per unit volume. Very good. Okay, now density of states means what? Please tell me. Number of energy states. States means here energy states only. Number of energy states per volume, per unit volume. Okay. Number of energy states. Here we are drawing. Suppose in this diagram, if you see, this is first state, this is second state, this is fourth, third state, this is fourth state, this is fifth states. Okay. Here we have drawn 5 states. Here we have done 5 states. Within these 5 states, we are calculating how many electrons are filled, how many electrons are available for conduction. Okay, that is we are going to calculate. Okay, that is also within the energy limits. This range we are calculating. Okay, so the density of states means number of energy states for unit volume. Okay, this you can calculate it. I am writing just direct formula. Okay, 4 pi by h cube and 2m to the power of 3 by 2 and e to the 4 of half. Okay, this you can calculate. This is equation 1. Let's take this is equation 2. Okay, so how you will calculate this equation? So you have to take momentum space. Okay, momentum space. Okay, like this you have to take. Okay, this is some kx, ky, kz. Okay, this kx means p is equal to, we know, h cross k. P is equal to h cross k. H is the Planck constant, p is the momentum, and k is the wave vector. From there you have to derive, you know, energy formula, right? E is equal to n square h square pi square by, or you can write this one also, you can write p square by 2m also, you can write p is equal to h cross k by 2m. Okay, density of states is given by, okay, for unit volume, this is unit volume, and number of states for energy. Okay, this you can calculate it. You will get the this formula, but this is no need to derive here. But if you want to derive, just you go through, you draw the energy momentum space. In that you draw the energy, you write energy equation. From there you derivate with respect to this vector, wave vector, that is k, dE by dk or dk by dE, whatever. Okay, from there you can derive this one. Okay, but we are writing only this formula. And what is the Fermi-Dirac distribution function? F of E. This you know. This you should know. What is the function? What is the Fermi distribution function? Don't know? You don't know? Are you there or not? Are you there?
Yes, sir.
Uh,
Yes, sir.
Not responding. This 502. Who is the? What is your name? 502. First time you responded. 502. 502. ఇప్పుడే
Yes, sir.
రెస్పాండ్ అయినా. ఏం పేరు?
శివశంకర్.
శివశంకరా?
Yes, sir.
ఏమైంది మరి? అసలే వస్తలేవు క్లాస్లకు అటెండ్ అవుతలేవు, ఏంటి ప్రాబ్లం ఏంటి?
కొంచెం హాస్పిటల్ పోయి ఉండే సార్.
ఓకే
వచ్చి.
ఓకే, ఆల్రెడీ ఫస్ట్ యూనిట్ అయిపోయింది. ఇప్పటి నుంచి అయినా రెగ్యులర్గా అటెండ్ అవ్వ క్లాస్లో. నువ్వు కంప్లీట్గా అసలు క్లాస్లే అటెండ్ అవ్వట్లేదు. ఓకే.
ఓకే.
యా. సో if you don't know also, you can no problem, but just respond. Okay, I'm not saying anything. Okay, the Fermi distribution function is 1 by 1 plus exponential E minus EF by KT, right? E minus EF by KT. This is Fermi distribution function. Okay, what it will gives the information? What information it will give? Probability of an electron to occupy an energy state. Okay, occupy an electron energy state. Okay, so energy state, this will give you the probability of electrons. Okay, occupation, how many electrons are occupied in this state. Okay, we have this much states here. If you see diagram, we have this much energy levels. States means nothing but energy states only, energy levels only. States means just you can energy states means energy state means energy levels only. So density of states means number of energy levels, number of energy states available for unit volume. Okay, in this density of states, in this available states, how many electrons are occupied? What is the probability of occupation of electrons in these states? What is the Fermi-Dirac expression gives information means what is the probability of occupation of electrons in these states, in these available states. That is the Fermi-Dirac distribution function means. Okay, so now equation, let's take this is equation 3. Equation 2 and 3 you substitute in equation 1. Okay, now we will substitute it. Okay, here small thing here we will consider. Suppose if it is above room temperature or just at room temperature, or if you take all temperature, if you take all possible temperatures, Okay, possible temperatures. EF always greater than, much greater than KT. So in that case, you can neglect this one because the second term value is higher than the first term, that is 1. Okay, this value is always higher than the this one. So you can neglect this one. Okay, you can neglect this one. So if you rewrite this Fermi-Dirac distribution function, f of E is equal, okay, 1 by exponential E minus EF by KT. Okay, EF by KT. Okay, I am rewriting again this expression, exponential minus, I'm bringing up, okay, E minus EF by KT. I am writing, okay, KT. Okay, we can write like this, right? Can we write?
Yes, sir.
Yeah, we can write. Okay, now this is equation 3. Just you substitute equation 2, that is density of states, and equation 3, that is Fermi-Dirac distribution. Just you substitute in the equation 1. Okay, equation 1 is density of electrons. This N means density of, okay, density of electrons, or you can say carrier concentration of electrons in the conduction. Oh, sorry, just a second. Notes is shared, disconnected. Just a second, please.
Okay.
Okay, N is density of electrons, that is we are going to write. N is equal to, limits are, lower limit is EC and upper limit is infinity, and this Fermi-Dirac distribution function is exponential minus, sorry, what is happening? So just you have to substitute these values. Once you substitute, you will just you do the integration. Just you have to integrate it, then you will get the complete answer. Okay. Now N is equal to integration EC to EF, EC to infinity, and the exponential minus E minus EF by KT. Okay, EF by KT. And what is the density of states? Okay, the density of states means nothing but available energy levels, 4 pi by h cube, 4 pi by h cube, 2m. Here m means electron mass. Okay, but we have to take electron mass, that is we are taking effective mass of electron. Okay, effective mass of electron, that I will explain what is the effective mass of electron. Okay, root 3 by 2. Here E power half. Okay, D. This is the expression we got. Okay, this is the expression we got. Okay, now here E is equal C. Here we have, suppose here we have electrons are there. The total energy is equal to kinetic energy plus potential energy, right? So here the kinetic energy is E. Okay, what is the lowest energy here? EC, right? EC, and potential energy, let's keep it as it is. Some height we are taking some height, that is we don't know. Let's keep it as it is. Okay, let's keep it as it is. Or you can say, just a second. Okay, just here the total energy of the electron is potential energy plus kinetic energy. Okay, if you take kinetic energy, or if you take, sorry, this is not kinetic energy. Okay. If you take kinetic energy of electron, okay, kinetic energy of electron, E minus potential energy. What is the potential energy here? This is total energy, and here EC is the lowest energy. This is height only, right? Here we are taking what we are taking. This is height only. Here suppose height, suppose this energy levels are, if you draw one dimensional box, what we have taken, this is the first energy level, this is second energy level, this is third energy level. Okay, right, 1 2 3 like that. These are some height from the ground state. The energy levels are separated some height. Okay, here also these energy levels are, we are taking as a potential energy. If you take kinetic energy of these electrons, you can write K is equal to E minus EC. E minus EC. Now, why we are taking kinetic energy here means we have to, how many electrons are available freely in the conduction band. How many free electrons are available, freely moving. That freely moving means that electron having some velocity, and if it is having velocity means that will have kinetic energy also, right? That's why here we are replacing E with E minus EV. E with E minus EV. Okay. Now this 4 pi by 2ME, this is constant value. Can we write outside of the integration? Can we
Yes.
write? Yeah, we can write. We will write this expression outside the integration because this is constant value. Okay, constant value. I am writing m star and 3 by 2 integration EC to infinity, and here E minus EC I am writing. I am replacing this E with E minus EC. Oh, what is happening? We are replacing EC E with E minus EC. Okay. Once we replace, just you have to integrate it. Okay. That's it. Okay. Just I don't know today it's sharing disturbance is coming. So E minus EC, E minus EC. Here 1 by 2 is there. You keep it like this, and exponential here E minus EF by KT. E minus EF by KT. Okay. Here derivation DE, right? So this is the expression. Okay, let's take other page instead of. I'm taking new page. Okay, then we can solve it freely. Okay, 4 pi by h cube and 2m e star by h 3 by 2 and integration EC to infinity E minus EC. Just I am replaced EC E with E minus EC 1 by 2 and exponential E minus EF by KT, right? KT into D. KT into D. Now, so how to solve this integration? How to solve this integration? Now, what will I do here? I will add one EC and I will subtract one EC in this expression. Here I will add and subtract. Okay, I will add and subtract. Okay, let's see what happens if I add and subtract. 4 pi by h cube, 4 pi by h cube, 2m star or me star by 3 by 2. Okay, EC to infinity and E minus EC of here exponential. Okay, otherwise I am writing E. I am multiplying minus 2 inside. Okay, here I am subtracting, adding and subtracting EC value. Nothing will change, right? Nothing value will change, right? Okay, now so we got like this. Okay, I am just again we will rewrite this expression. Here I am writing this expression again. So we can we write here E minus EC by KT plus exponential E minus EF. Can we write? Can we
Yes,
write like if you take minus here? Okay. Can we write like this? Sorry. Just a second, please. Just a second. This is not okay. Exponential. We are writing EC is constant and EF is constant. These are not depending on DE. So we will write that terms in separate. Okay, that is EF minus EC by KT. Okay, these are independent of energy. So exponential again we are writing E minus EC. I am taking here minus out. So we can write like this one and this one we are writing. Okay, by KT. Okay, D, right? Here same thing we will write E minus EC by half and here integration EC to infinity. Same thing you write here 4 pi by h cube and 2m E by to the power of 3 by 2, right? So here this term is independent of energy, right? Only here independent of energy means there is no E term, isn't it? Only E is in first term only E is there, in third term only E is there. In the second term there is no E. So can we take out of the integration? Can we take out of the integration?
Yes, sir.
Yeah, we can take out of the integration 4 pi by h cube and 2me by 3 by 2 and I am writing this is not depending on energy, so I am writing EF minus EC by KT. Okay, just it's almost done. EC to the 4 of infinity and E minus EC to the 4 of half and exponential minus is there common E minus EC by KT into DE, right? So this is our final expression. Okay, now if you know direct formula, you can write it. But if you don't know formula, what we will do here, this is it is a constant. Okay, it is constant value. Forget this one. Okay, here we have to integrate this expression. Here we have to integrate. Okay, for simplification, we are taking E minus EC is equal to, we are taking X. Let's take X. We don't know direct formula, so just we are converting into X, then it will become a easy. Okay, now we are taken E minus EC is equal let this is E minus EC is equal to X. Now DE is equal to what is the value? This is constant, EC is constant, right? So this is B 0 and dx. That means DE is equal to dx, isn't it? DE is equal to dx. Just here you substitute X and we are replacing. So just a second. So this is simple integration only, but you have to just go through once. Okay, here limits. So limits also, if you change this term into X, DE in terms into X, limits also we have to change, right? So here E minus EC is equal to X, right? So what is the upper limit, lower limit? So you have to convert limits also into X. So what is the lower limit and upper limit? EC minus infinity, right? First you substitute EC here. So EC minus EC, EC minus EC 0. That means lower limit becomes 0. And what is the upper limit? Infinity minus EC is equal to X. What is the value here? What is the X value here?
Infinity.
Infinity, very good. Okay, so our limits also changed 0 to infinity. Earlier EC to infinity, but we changed limits 0 to infinity. Okay, here 0 and infinity, and E minus EC is equal to X to the 4 of half, and here exponential A X by X by KT. Just we have substituted E minus EC is equal to X and DE is equal to DX, right? Now expression turns into in this equation. Now formula is here. What is the formula? Do you know this formula? Do you know formula? If you don't know formula also, no problem. E to the 4 of X dx. What is the formula? Do you know? Don't know? Root pi by 4a cube. Root pi by 4a cube. This formula is root pi by 4a cube. Just you solve this one. What you will get here? A means what here? What is the A here? What is the
minus
minus?
Minus 1 by KT. Constant.
Already minus is there, here minus is there. A means here 1 by KT. Now our integration turns out root pi by 4 into A means 1 by KT, right? 1 by KT, here cube is there, right? Okay. Now we got the integration this much. Okay, this value will in the equation only we are deriving this one. So we will write the total expression for n is equal to 4 pi by h cube and 2me star 3 by 2 and our exponential minus E minus EF minus EC by KT, EF by KT, and this is the value, right? 4 pi by 2 into here KT cube, right? KT cube 3 by 2, isn't it? Can we write like this? KT in the denominator I bring out, okay, 1 by KT means it will come to the numerator, right? Is it
Yes,
correct or
sir.
not? Okay, now this 2 and here 1 2 will cancel out. Okay, 2 pi 2m here we can write kt, right? Kt also 3 by 2 power is there, here 3 by 2 power is there, you can write totally. Okay, 2 pi by h cube 2m, okay, 3 by 2 exponential, I am taking minus out, okay, ec minus ef by kt, okay, ec minus ef by kt. This is the density of electrons in the conduction band. Okay, density of what, just I will take 1 minute. Okay, it's a 1050, but I will take 1 minute. Okay, this is n, you can write nc exponential minus ec minus ef by kt. Okay, this why I taken here minus common, so it is convenient, for convenient only I took. Okay, because if you see, this is a intrinsic semiconductor, this is EC and this is Fermi level, right? So which one is higher here? EC is the highest energy, right, compared to EF, isn't it?
Yes, sir.
That's why I'm writing EC minus EF. You can write EF minus EC also, it's not a problem. So NC is the effective density of the charge carriers. You can write NC is equal to 2 pi by h cube 2m e by kt to the 4 of 3 by 2 to the 4 of 3 by 2. This is the density of effective state, effective density of states. This one NC means effective density of states. N is the charge carrier density in the conduction band. Okay, we are calculated electron density. Where we will get, where we will have free electrons in a semiconductor, in a conduction band, right? That's why we have calculated free electrons in the conduction band. That is N is equal to NC exponential minus EC minus EF by KT. EC minus EF by KT. This is expression. Okay, just what we have done, the density of electrons or available electrons in the conduction band is we have energy states, that is we have like energy states in the conduction band. So these states are extended EC to infinity. Okay, these are all energy levels. Within these energy levels, we can, how many electrons are there, we don't know. To estimate that electrons, we have considered all energy levels and probability function, that is occupation of electrons in a energy state, and density function, that is number of available energy levels. Okay, number of available energy levels. Within that energy levels, how many electrons are occupied, that is the number of density of electrons means. Okay, or charge carrier density means. Okay, you got it right, what we have calculated?
Yes, sir.
Just here we have a energy levels in the conduction band. Okay, this is conduction band. Here we have number of energy levels. Within this energy levels, here some free electrons are there. How many electrons are there, we don't know. That electrons we have estimated. Okay, that is the formula is given by this expression. Okay, today I will stop here. Tomorrow we'll discuss density of holes in the valence band. Density of holes in the valence band.